This is your last set of math notes that you will take for your senior year of high school. You made it. All right, so we have 2 examples to get through. So we are doing example 5 and example 6, and then you have officially completed high school Trig class after you maybe take your exam if you have to take your exam. So, example 5 is what we are going to get into. So again, kind of same thing as yesterday, as far as you already know your answer. You're just trying to get to that answer using all of your trig identities. So for example 5, example 5 says verify that tangent squared x minus sine squared x equals sine squared x tangent squared x. So even though they look very similar to each other, they are not the same thing. So I actually have to prove that they are equal to each other. So for your first, and it really doesn't matter which side you're trying to get to equal to the other side. I'm going to try to work with this side and make it equal to this side. You already have the same similar things in your answer. However, one is subtraction, one is multiplication. So I need to figure out how I'm getting there. So your tangent squared x. The first thing I'm going to do, tangent squared x is a quotient identity. So I'm going to change it to sine squared x over cosine squared x. So again, that is a quotient identity. It says tangent is equal to sine over cosine. Then I have minus sine squared x from here. And I know that I just got rid of the tangent and I need a tangent. But I have to work to that part. From here, I am ultimately subtracting. Because I'm subtracting and there's a fraction, I need a common denominator. So my sine squared x over cosine squared x already has a denominator of cosine squared x. So I'm going to make this have a denominator of cosine squared x, which means I have to multiply the top and the bottom both by that. So I have sine squared x over cosine squared x minus sine squared x times cosine squared x over cosine squared x. So all I did was make a common denominator to try to verify that one side is essentially to actually be able to subtract them. So from here, I'm going to rewrite this as one whole thing. Okay. So that's all I've done at the moment. From here, I am going to kind of look at what I have in order to get back to what I need. Meaning your numerator, they both have a sign in them. So I am going to look at factoring this out. So whenever I factor this out, they both have a sine squared x. So I'm going to rewrite this as 1 minus cosine squared x over cosine squared x to get to here. So these both had a sign. I factored it out to end up at that point. From here, and I know this is going to look weird, but we're just not going to multiply it. So I have a 1 minus cosine squared x. 1 minus cosine squared x is a trig identity that says sine squared x plus cosine squared x equals 1. So this is a Pythagorean theorem identity. So I'm going to change this to sine squared x. I know that at the moment doesn't look like it helps me. However, I know my two numerators are the same and I could multiply them together. However, my end goal is to end up with a sine squared x. I currently have one of those. And then to end up with a tangent. If you look at your quotient identities, and we actually use this one up here, is that tangent is equal to sine over cosine. So I can change, instead of combining my sine squared times my sine squared, I'm going to leave them separate. So this part I can change to a tangent squared x. So I would end back up with sine squared x times tangent squared x, which is my goal. Okay, so weird process, dealing with the same like sine, cosine, tangent over and over again, but that is how you would get to your answer being multiplication. All right. Why this is at the very end of your notes, I don't actually know. However, this is kind of a suggestion on how you can go about solving trig identities. It's really just telling you, like, work with the simpler side. You already know the answer. Change stuff to sine and cosine. Use your identities. Rewrite stuff. Factor stuff. Blah, blah, blah. Your last example is using your calculator to test whether each equation is an identity or not. And then it says, if it appears to be an identity, verify it. And then if not, find the x value for which both sides are defined but not equal. So I'm not going to ask you to do this last part as far as like finding the x value. You really need to prove that they're the same and then verify it. And then if it's not the same, I just want you to write like they're not the same. You don't have to do that added part as far as like finding the x value that makes them to where they're both defined. So what this question looks like is you need your graphing calculator. You are going to plug in not the entire equation at once, but you're going to plug in, so you're going to go to y equals and plug this in to one of them, and then go to y equals and plug this into the other one. So you're graphing both of these. For those of you that have colored graphs, do them at the same time. You'll see it will be very obvious that they're the same or they're not the same. They're either going to overlap each other or they're going to look totally different from each other. So whenever you plug this very first one into your calculator, you're going to get something, and I'm going to just sketch it to the best of my ability. You're going to get something that looks like this. Whenever you plug tangent into your calculator, you're also going to get the same graph. They should overlap each other. They look the same. This is how you are going to tell whether it is an identity or not. So everything that we've done up to this point, like it's telling you it is an, like this is equal to this. Prove it. This is now saying like these might not actually be equal to each other. So use a calculator to see if they actually are. If they are, then verify it. But if not, you can't verify it because it's not equal. So that graph should look familiar to you. It's a tangent graph. We've looked at that. So because they are the same thing, I have to actually now prove that they are an identity by actually working it out. So I'm going to take this side and I'm going to prove that this side is equal to tangent x. So for the top part of my problem, the 1 plus tangent squared x screams Pythagorean theorem identity. So 1 plus tangent squared x is equal to secant squared x. Then looking at your denominator, I'm going to leave it like that for right this second, because I now have a secant squared x over a cosecant times a secant, which can simplify. So now I just have secant, not squared, I just have a secant x over a cosecant x. Thinking about reciprocal identity, secant is the reciprocal of sine, cosecant is the reciprocal of sine, and then secant is the reciprocal of cosine. I have sine over cosine, so this was reciprocal identity. This is then quotient identity. Sine over cosine is equal to tangent, which is what I have. So I got back to what my goal was. Looking at part B, you're going to do the same thing. You're going to go to your graph, type in y equals, plug that chunk in, the other side, do y equals, plug that chunk in. You will see whenever you graph them that this looks like this, kind of just pretend that mine looks like your graph does, and then this looks like this. They are not the same, which means they are not identities. If they are not identities, there's no way to verify that they are, because they're not. So again, this part of the direction, don't need you to do. If it is an identity, then verify it, which you did in part A. If it's not an identity, just write not an identity, and you're done with your problem. So that was it for chapter 5, lesson 2. That is your last set of notes. Yay, you, celebrate, whoop whoop. You made it this far, so yay.